Okay, so yeah, with the pad cluster, I didn't put our affiliations there. I'm Henrik from CETA, this is John from Lund University, and then our GC Wiz here from Technical University of Munich, Eike Schling. So, our take on this theme, or this year's Smart Geometry theme, was to look at the mathematical language and see how do mathematics work with uncertainty. And that is, of course, through probability theory. And we want to see how we could apply this to architectural form finding and urban design. So the way we did this was to take a parametric model, but view the uncertain input parameters as probability distributions with an estimated mean and standard deviation. So this is, of course, the very common normal distribution with mean in purple and standard deviation in orange here. So what we did then was something that's in engineering called Monte Carlo simulation. We drew samples from these input parameters, or input distributions, I should say, and optimized a parametric model with a certain performative measure for all of these hundreds of samples that we draw from, and then create the output shapes like a collected form of, or a collected set of probabilistic output shapes. Yeah, this is participant work here. I don't know how well you see it here, but it's we have uncertainty in the height of adjacent buildings, like future adjacent buildings of a certain site. And here, I think it was the performative measure was solar axis, and we optimized for solar axis here. And from all these uncertain heights, we got a cloud of probabilistic shapes or envelopes out, and then found the mean and the standard deviation in this shape space. Oops, sorry. This is just cuts the sections through this shape. So, of course, doing optimizations, not only once, but like hundreds of optimizations for different contexts, is a huge computational task. But what we gain from this is that we're not only optimizing for a specific case with a peak performative measure, but we're actually optimizing for all probable situations and also taking in their different probabilities. So it's kind of a soft optimization, I call it, like we're optimizing, but with probability in it. So this was on the building scale, but this could of course be applied on several scales. In engineering, for example, probabilistic design is a quite standard thing, looking at risk analysis and sensitivity analysis for structural components, for example. We went the other way instead and looked at the urban scale and made an urban model, a pretty simple urban model, which we could draw samples from. So in this model, it's just the building heights that are distributed. So here is just drawing samples from this kind of parametric urban model. It's kind of a little bit too big variation here in this this system. What I imagined in the beginning when we started working with this was actually to have it really parallel between the urban and the building scale and look at, for example, population growth or economical parameters as input parameters. These, of course, then being very uncertain and making estimations on these, and then look at the evolution of urban parametric model from this. after a while, we actually started in got a quite different starting point. We started looking at space syntax measures instead and saw how that informed our parametric model. And there's also a probability theory in this, because it's kind of a top-down model in some sense, that we draw a certain network and look at the space syntax measures on this, in this case, integration measure. But then our integration measure shouldn't like deterministically decide how our model becomes. It just suggests, it just gives a probability of a certain outcome of the city making this kind of street network. This, I don't know how well you see it, but this is centered around the Barking and Dagenham area in East London, and we especially looked at the riverside part here. So that was the site for this workshop project. Here we just added a bridge over the Thames and saw that changed the integration value here. So before the workshop, we developed a simple tool just to be able to draw networks in our parametric modeling software and find the integration value and then build our probabilistic parametric model out of this. There are quite strange color scheme here, but what you see as orange here is the normal red in like highly integrated, and purple is the blue, like less integrated streets. And from this then we get the urban massing here. This is actually participant work also. This is Alessio Lombardi's work on adding to this model, and he worked on a way of looking at the integration values and by probability, the probabilistic means placing squares in the model. So you also see that there's a smaller plot size around the square and a higher building height. So it's high land values in this area. We also had a goal of having a technique for an iterative process for program distribution here. So that would also inform our building scale project, but we didn't come that far here. The workflow was here then to work with this model, extend it with some new functionality, and then zoom down to a specific point here or a specific site and do the building scale probabilistic modeling there. So the questions we wanted to pose to the participants here was then how to use this data that we get out. We get a cloud of like probabilistic shapes out, if you look at the building scale. And how do we use that for a specific design intent? Do we apply the mean solution, or do we apply the extremes? Or what is the logic in choosing different parts? And how does that relate to our specific design problem? Could we inform other things than just the shape? Could it inform organizational or programmatic parts of the project? Which kinds of uncertain parameters do we use? And also which kind of performative measures do we use? This of course depends very much on the specific project that we're looking at. But I mean, this is a very, as you see, it's a very general thought, just using probability theory in design and architectural forefinding. So we of course just had to focus on a very small part of this general thought. But yeah, I think we succeeded in a way that we participants actually added more performative measures that we hadn't brought to the table, and we're going to look at some participants' works here now. So this is just a geometry study of the one chosen parametric model. This is what we saw before, so that that was the geometry for this building. I think this is really interesting because when you're doing optimization, especially like huge optimization sets that we did, it's very important that you try to understand as much as possible the problem that you're facing, or what your kind of space that you're actually looking at. So in this project, the participant actually did a grid in the solution space and plotted the results on this to see if it was a really simple optimization problem that could be solved only by a hill climbing algorithm or something like that, and also to see like which area should I do the more detailed optimization on. So this is a movie here. Let's see. Yeah, it just goes through some optimized forms. It is a quite big spread here, so I think the problem should have been set up a bit a bit more tight, and also maybe gone a bit further in the optimization to really find the true optima. But it's really a work in the right direction here. And some suggestion for a building from this. This is Susan Verma's work, another participant, looking at street networks from first like just general connections, like much in the line of thought from the previous talk here, volatile territories. But then also looking at how the space syntax measures played in this kind of network, and then used the parametric urban model to make a massing suggestion and sampling from this one, taking a site in this model and then optimizing for a site here. Let's see. So this goes through, you see, it's changing context down here. It's actually an error in this because all the buildings are changing in the same direction. There's the same random seed in every building, or the same random value actually in every building here. So it should be changing and not in tandem like this. But you see how it works through lots of different samples and optimizes for every context there. Yeah, so this is just a plot of the optimization going on there. And these are some outputs of the solution space there in the optimized form with some different physical instantiations. Just the area playing with the space syntax measure to find a good street network. This is the same project as the space syntax study there. This is Joel Letkeman's project, looking at pretty unusual typology for a building, but optimizing on solar axis in this kind of cube building with all the cubes possible to move, and optimizing the placing of these cubes. And then the aggregated probabilistic form coming out of that in a physical form. This was Alessio Lombardi's work, looking at not then solar axis, but view optimizations, and not with building height uncertainty, but adjacent building placement uncertainty instead, and trying to optimize the views here. I think this was really nice work, but it didn't come really to the point of making any large optimization schemes here. So there is no real solution space built, but it's on a very good way, I think. This was Peter Hertog's project, not at all looking at the environmental analysis, but actually taking the integration measure and using, trying to optimize the integration divided by floor area for a specific building in a block here, are actually trying to equalize that ratio with the ratio of the other buildings. So the other buildings were we took samples from this urban distribution on the other ones and simulated this. So this was a totally other measure to use. Yeah, and there's some more data on that. Yeah, this is some other work on shapes, and this didn't come. There's some optimization, but it didn't really come to the full solution spaces either, but on a good way, I think. What we're showing on in the exhibition here is 3D prints of some of these like solution spaces that we got. It's more of, we see this more as like analytical studies of of the probabilistic space that comes out. But it's the interesting thing here, I think, is then to think more about how what parts of this solution space to actually use and how to instantiate it physically or organizationally or programmatic. I would like to thank Tim Stuner and Stephen Law from Space Syntax, who's been our collaborators in this also, and also Volker Müller from Bentley, who's been a software consultant for us. Thank you very much.